Hello, welcome to the lecture for Chapter 7, Memory. Just a chapter overview. We'll be studying memory, building memories, specifically encoding, memory storage, retrieval, which is getting the information out, forgetting, memory construction errors, and ways to improve memory. Studying memory. We use what's called an information processing. So memory is the persistence of learning over time through encoding, storage, and retrieval of information. The information processing model compares human memory to a computer's operation. It assumes that in order to remember, one must indulge in encoding, storage, and retrieval of information. Stages in the information processing model. First is encoding, getting information into the memory system. You will never have a memory of something you never had any experience with. Storage. This is the retaining of the encoded information over time. It has to get into the brain and find a home there, basically. And then retrieval. You have to get the information out of storage. There can be problems in any of these things, the encoding phase, storage, or retrieval, before information is processed well or is made into a memory. So the stages in forming memories. So first you have to experience the information at some level with your senses. Then you have to process that information in what's called the short-term memory, where it's encoded through rehearsal. And then the information needs to be moved into long-term memory for later retrieval. This is a modified three-stage processing model of memory. Atkinson and Shiffrin's classic three-step model helps us think about how memories are processed, but today's researchers recognize other long-term memories form. Other ways long-term memories form. So first, you have something happening in the world. Now, if you see the line going along the top, it could happen automatically processed into long-term storage without even really being aware or without even experiencing it with any of your senses or working on it in long-term memory and it getting encoded into long-term storage that way. There is another way that we most likely are aware of because it's not automatic. This involves some kind of sensory input coming into your experience. This then gets encoded when you pay attention to important or novel information as well. Then you can reinforce the memory in short-term or working memory by rehearsing and active maintenance of the information, which then makes it go into long-term storage. You can retrieve it from long-term storage to use it in your working memory. And working memory is the pathway that you also store memories in long-term storage. So let's talk about working memory. This is a newer understanding of short-term memory. It includes conscious and active processing of incoming auditory and visual spatial information. Auditory is just things you hear. Visual spatial is things you see in this 3D world that we live in. Information retrieved from long-term memory. And it also works in the opposite direction, like I mentioned. It processes already stored information. And information enters the working memory through vision and auditory rehearsal. Just simply trying to, the more likely you are to see it, the more likely it enters into memory, and the more that you rehearse it out loud, or the more you experience it out loud, the more it goes into memory. So let's quiz ourselves. What are two basic functions of working memory? active processing of incoming visual and auditory information, and it's also focusing our spotlight of attention for what we're thinking about, what we're doing in the moment. How does the working memory concept update the classic Atkinson-Shiffrin three-stage information processing model? Working memory is the active processing from Atkin and Shiffrin's short-term memory. They're the same thing. While the Atkin-Shiffrin model viewed short-term memory as temporary holding space, working memory plays a key role in processing new information and connecting it to stored information. So building memories through encoding. Our two-track memory system, automatic processing and implicit memories, and effortful processing and explicit memories are things that I'm going to talk about with encoding. So first, the two-track memory system. There's something called implicit or non-declarative memories. This is the retention of learned skills or classically conditioned associations without conscious awareness. It is formed with automatic processing. So it's sort of implied to become a memory, if that helps you remember things. Explicit or declarative memory is the retention of facts and personal events that can be consciously retrieved. It's formed via effortful processing. So you have to be mindful of what you're doing to make it happen, basically. That's what effortful processing is. Automatic and effortful processing. Just to talk a little bit more about them, automatic is the unconscious encoding of everyday information and well-learned information. It happens when you drive the same route to work every day. You learn that that stop sign is there and that building is there and that person tends to be there. So there are things that you didn't really try to learn, you just learned because from repeated exposure, it just became your cognitive map of what the situation was. And then there's effortful processing. This is encoding that requires attention and conscious effort. It may just be that you draw your attention to something and it becomes a memory without really trying really hard to remember it, or you may have to spend some time trying to get it in. But anyway, there's some type of effort that needs to be drawn, and that's the difference between automatic and effortful processing. So building memories. Automatic processing and implicit memories. Implicit memories include automatic skills and classically conditioned associations. So these are things that don't require any active cognitive processing on your part. Could be information about space, time, and frequency, and it can be processed without conscious effort. Effortful processing and explicit memories involve explicit memories becoming automatic with experience and practice. That's like when you first try to learn how to play the trumpet. You have to think about it very hard, but then at some point it just becomes automatic. Sensory memory, the first stage in forming explicit memories. You record immediate and very brief information, and it's fleeting in nature. So it's there right away, but it doesn't last for very long. There's something called iconic memory. It's picture image memory of a scene. This is perhaps something that happens when you, maybe you have a memory of what happened during the 9/11 situation, and you remember what those buildings looked like or where you were. That's the picture image memory of a scene. Then there's echoic memory. This is sensory memory of sounds. So you recognize a certain song because it's your favorite because it is there in your brain as an echoic memory. So we'll talk about total recall briefly. When George Sperling in 1960 flashed a group of letters similar to this one for 1/20th of a second, that's pretty short, people could recall only about half the letters. But when signaled to recall any one row immediately after the letters had disappeared, they could do it with near perfect accuracy. So that's that you have it for a brief moment, and then if you don't do anything with that information, it goes away. And they probably could just see one, or could only focus on one row, and that's why the one row is something that they could remember. Capacity of short-term and working memory. So about short-term memory, Miller proposed that individuals can store about 7 bits of information during the short-term stage. Other researchers confirmed that individuals can recall about 7 digits, or about 6 letters or 5 words, without distraction. For working memory, that capacity varies with age. Work is more efficient when individuals focus on one task at a time without distractions. Unless rehearsed, verbal information may be quickly forgotten, like I mentioned. So you look at this graph with along the x-axis, or the one going from right to left, you see time in seconds between the presentation of consonants and the recall request. So they gave them a consonant like C, and then they asked them to recall what they just told them. And then on the y-axis is the percentage who recalled the consonants correctly. You see that as time's lapsed, they really couldn't remember what letter they had just been told. Excuse me. But if they're asked right away, they had almost 100% accuracy in what letter was told to them. So there are some effortful processing strategies to help improve encoding in memory. There's something called chunking. This is organizing items into familiar and manageable units. This occurs naturally. So when we chunk information, we organize information into familiar, manageable units. So glance for a few seconds at row 1 in this figure. Then look away and try to draw those forms. It's pretty difficult, isn't it? But you can easily reproduce row 2, which is just as complex. And row 4 is probably much easier to remember than row 3, although both contain the same letters. So chunking information helps us recall it more easily. Another effortful processing strategy is the use of mnemonics. They're memory aids. This includes techniques that use vivid imagery and organizational devices. You may remember from math class the mnemonic, "Please excuse my dear Aunt Sally." The first letter of each of those words corresponds to the first letters of the order of operations that you need to use in math. So please is parentheses, excuse is exponents, my is multiplication, dear is division, aunt is addition, and Sally is subtraction. You're welcome for this wonderful image of your dear Aunt Sally. So let's quiz ourselves. What's the difference between automatic and effortful processing, and what are some examples of each? So automatic processing occurs unconsciously or automatically for things such as the sequence and frequency of a day's events and reading and understand words in our own languages. Effortful processing requires us to focus attention and make an effort as we work hard to learn new material in class or new lines for a play. Spaced study and self-assessment are two other ways to help. The spacing effect is the tendency for distributed study or practice to yield better long-term retention that can be achieved through math study or practice. So what this says basically, if you study 15 minutes today and 15 minutes tomorrow and for 15 minutes for the next 5 days or however long, instead of just studying, let's say, an hour or whatever the addition of the 15 minutes series is, that you'll actually retain the information better than just cramming it all into one study session. It produces better long-term recall than mass practice, which produces speedy short-term learning and feelings of confidence. So you might feel like you have it right away, but then it leaves your brain pretty quickly if it's not reinforced. And the idea here is that the more often you encounter the information, your brain says, hey, that's something I need to keep track of. That seems to be important. On the flip side, if it's something that you only encounter briefly, your brain puts less emphasis on it and is less likely to remember. I'm not saying that you won't or can't remember it, it's just saying it's not as likely. So why not take advantage of the way your brain works and distribute studying over time? The testing effect is that there's enhanced memory after retrieving the memory rather than simply rereading information. So if you have to come up with that information from memory, it helps strengthen the memory. Again, your brain thinks, oh, this is information that's needed in the future, so I'm going to strengthen that association. This is referred to as the retrieval practice effect or test-enhanced learning. It's an effective method for distributed practice. It also helps improve learning. This is why I keep asking you these little quizzes every now and then during the lectures. It also helps to make new information meaningful. Spaced practice is most effective when new information is meaningful. Encoding errors, so getting it into your brain the right way, can be avoided by translating what is seen and heard into personally meaningful terms. Herman Ebbinghaus estimates that compared with learning nonsense material, learning meaningful material requires 1/10 of the effort. This is also why in the exercises that you do for homework, I try to pick things that are meaningful or things that could potentially be meaningful to you so that the information that you're trying to learn is easier for you to remember. You're welcome. So let's quiz you. Because we just said quizzing helps you to retain the information better. So what strategies are better for long-term retention? Cramming and rereading the material, or spreading out learning over time and repeatedly testing yourself? Although cramming and rereading may lead to short-term gains in knowledge, distributed practice and repeated testing will result in the greatest long-term retention. So let's talk about memory storage. This is retaining information in the brain. And this happens through synaptic changes. As we said in chapter 6, the synapses are when you have two neurons basically communicating to each other to have an electrical impulse travel. Retaining information in the brain. The capacity for storing long-term memory has no real limit. You may feel like sometimes your brain is full. I know I do. But there's really been no one's been able to reach a maximum amount of learning that they can store. With the research findings, information is not stored in a single and specific spot. Perception, language, and emotions require brain networks. many parts of our brain interacting as we encode, store, and retrieve information. It's like a big web of neurons that when you say one thing, it lights up a certain path, and when you think about another thing, it lights up another path of neurons, and some of them may or may not have some paths in common. But it's sort of this big web of neurons that get activated based on relevant information. So the explicit memory system involves the hippocampus, which is a part of your brain. You'll learn in chapter 2, but I'll also show you a picture in a little bit. So explicit and conscious memories are either semantic or episodic. Semantic memory is explicit memory of facts and general knowledge. So your name, what color is the first color in the rainbow, things like that. Episodic memory are explicit memories of personally experienced events. So it's like an episode of your life, if you want to help that remember. The hippocampus acts as a loading dock where the brain registers and temporarily stores aspects of an event. So you could say the memory camps out on a hippo to get it into information. I don't know. Making it relevant and meaningful is helpful, so I'm just trying to make that happen for you. So here's part of the brain that has the hippocampus in it. That's the whole brain that you see, the green thing, or at least an image of it. And in that inner area is where the hippocampus is. Explicit memories for facts and episodes are processed in the hippocampus. That's the orange structure. And they're fed to other brain regions for storage. So explicit memory system also involves the frontal lobes. Memories migrate for storage via the memory consolidation process. Left and right frontal lobes store different information. So these are again parts of your brain. The right stores episodic information and the left stores semantic information. And remember, episodic are those things about like little episodes of your life, and semantic are little facts like what your name is. A good night's sleep supports memory consolidation. So the hippocampus and the brain cortex display rhythmic patterns of activity during sleep. That's when researchers think your brain is taking all the memories that happen through the day and encoding them into memory, long-term memory. This is a fun little bird detail. Among animals, one contender for the champion memorist would be a mere bird brain, the Clark's nutcracker, which during winter and spring can locate up to 600 caches of pine seed it had previously buried. So it stores some good memories. Implicit memory system involves the cerebellum and the basal ganglia. So we've got a picture of a section of the brain, basically cut in half, like you started at your forehead, the middle of your forehead, and cut backwards. Obviously, don't do this. The cerebellum is like at the back of your head. It's that little orangey thing in the picture here. And the basal ganglia, you can see in the picture, are those areas right outside the blue. The hippocampus is also labeled here, and the frontal lobes, which we were talking about just a little bit ago. So the cerebellum extends from the rear of the human brainstem. The brainstem is just like it sounds. It's a stem, just like an apple, that comes away from your brain. It plays an important role in forming and storing memories created by classical conditioning. So the cerebellum is where you learn things automatically or implied. That's why it's called the implicit memory system. The basal ganglia is a deep brain structure involved in motor movement. So this helps form memories for physical skills, which are also implicit memories. So if you're learning how to dance or how to ride a bike, this is where the information is stored, in your basal ganglia. So just to quiz yourself, which parts of the brain are important for implicit memory processing, and which parts play a key role in explicit memory processing? Answer: for implicit memory processing, it involves the cerebellum and the basal ganglia. For explicit memory processing, it involves the hippocampus and the frontal lobes. Another question: your friend has experienced brain damage in a car accident. Hopefully that's not the case. That's terrible. He can remember how to tie his shoes, but has a hard time remembering anything you tell him during a conversation. How can implicit versus explicit information processing explain what is going on here? The answer is that implicit memories are skills and classically conditioned responses, such as tying your shoelaces. And explicit memories are facts and episodes. Because implicit memories are intact but not explicit ones for your friend, it's likely that the hippocampus or frontal lobes are where he sustained damage in the accident. There are also effects of emotions on memory processing. Hopefully you're not feeling like the guy in this picture. Excitement or stress triggers hormone production. It provokes the amygdala, which is another part of your brain, to boost activity in the brain's more memory-forming areas. The resulting emotions persist with or without conscious awareness. So it's like stress or excitement hyperactivates a memory being encoded. The effect of emotions on memory processing. There's something like a flashbulb memory, which is a clear memory of emotionally significant events. Like I said, you may remember this picture about the Twin Towers being bombed, well, being blown up by airplane. These type of flashbulb memories that pop into your brain and stand so strong occur because of these emotionally triggered hormonal changes. And they're retained because you think about them. The more you rehearse or think about it, the stronger the association, and the more likely the memory is to be something you can pull from your brain. So just to review key memory structures in your brain, the frontal lobes and the hippocampus are involved in explicit memory information. The frontal lobes are on the front part of your brain. It's the left in this picture. And if you put your hand on your forehead, on the other side of your skull is your frontal lobe. Remember, explicit memories involve the retention of facts and personal events that you can consciously retrieve, also called declarative memory. The cerebellum and the basal ganglia. So the cerebellum is that thing at the base of your skull, at the back of your head. And the basal ganglia basically are those, the part in the middle structure. It helps with implicit memory information. And remember, implicit memories involve the retention of learned skills or classically conditioned associations without conscious awareness. They sort of happen in implied fashion. And the amygdala, which is that purple thing in your picture that you're looking at, is where emotion-related memory formation gets involved. As I mentioned before, there are a bunch of neurons in your brain, and they are together in like a web, and this is called a neural network. Again, we'll We'll cover more of this in chapter 2. However, basically neurons are chains of little cells that carry information from one part of the brain to another. And the synapse is a structure that permits a neuron or nerve cell to pass, it's that space in between neurons, to pass an electrical or chemical signal to another neuron. So it's like it could be like a cool firework display if you actually had the lights involved. So this picture is kind of neat in that it shows you, this is a simplified version of a bunch of neurons together. Your brain is a lot more complex than this. But it just has, it's a webbing of neurons, and it's not like they're in a straight line. You know, one can connect to this one and that one, and one can connect to, it's just amazing when you think about it. That's one thing that just blows my mind, is the fact that our mind has so many different neurons that create this complicated network that gives us this advanced thinking. It's pretty cool when you think about it. So let's learn about synaptic changes from Kendall and Schwartz. They were studying slugs, as you can see from this little guy here, and they pinpointed changes in neural connections. There was more serotonin, which is a hormone in your brain that gets released during learning. The cell synapses, which we talked about, is that space in between that allow communication between neurons. The cell synapses become more efficient, which increases the efficiency of the neural networks. So here, serotonin seems to be driving learning, which is pretty cool. And the number of synapses increases with experience in learning. So the more that you study one specific thing, or the more that you are experienced with something, the synapses are stronger and happen more often. So there's something called long-term potentiation, or LTP. This is an increase in a synapse's firing potential. It's believed to be a neural basis for learning and memory. After long-term potentiation, a current passing through the brain could not erase old memories. It's like solidifying or codifying the memory, if you will. It's not like your neurons become stiff, it's just that it's so strongly established in memory once long-term potentiation has happened that even passing current through the brain doesn't impact those memories. So just to talk about our two memory systems, we have memory processing, the things that happen automatically on the blue or the left side. These are implicit memories or non-declarative, and they happen without conscious recall. So you don't even realize that it's going into your brain. It's processed with the cerebellum, remember that little lump thing in the back of your brain, and the basal ganglia, which is somewhere in the middle. It's information about space, time, and frequency, like where you ate dinner yesterday. It involves motor and cognitive skills, like riding a bike, and classical conditioning things, like a reaction to the dentist office, which could be good or bad. But I have to say, there was one time I went and there was a new dental hygienist, and she used this, it's like a sandblaster water pick thing on to clean my teeth, and it hurt so much. When I saw her the next time, I winced. I classically conditioned that seeing her was terrible, but thankfully, when I saw her the second time, she did not use that, and she used the regular scraping technique. I don't know exactly, but I've learned that she's not a bad person. Okay, so then also for memories, there are effortful ways to learn memories. Excuse me. These are explicit memories or declarative memories, and this involves conscious recall. They're processed in the hippocampus and the frontal lobes. Remember, the frontal lobes are in the front. And do you remember where the hippocampus was? Semantic memory and episodic memory are the two memories processed here. Facts and general knowledge are part of semantic memory, and so these chapters' concepts. And the episodic memory are personally experienced events like family holidays or your last vacation. Oh, I shouldn't have left you hanging. If you remember, the hippocampus is actually back by the cerebellum in the back of your brain. So, to quiz yourself again on something, which brain area corresponds to stress hormones by helping to create stronger memories? The amygdala. It was that little purple thing. It's not really purple in your brain, but it's right at the top of the base of the brainstem. So increased efficiency at the synapses is evidence for the neural basis of learning and memory. This is called what? Long-term potentiation, or LTP. So retrieval, or getting the information out of your brain. This measures your retention of the information, and we'll also talk about retrieval cues to help get the information out. Measuring retention. So recall. Memory demonstrated by retrieving information learned earlier. For instance, a fill-in-the-blank test. You have to remember the specific information. Other than the sentence around it to give you clues, if it's not in there well, you're not going to recall it very easily. Recognition is memory demonstrated by identifying items previously learned. So for instance, a multiple choice test. The answer's in front of you. At least you just had to study well enough to be able to recognize which one is the right answer. Relearning is memory demonstrated by time saved when learning material for a second time. Just like it sounds, it doesn't take as much time to relearn something because you already learned it once. Those associations are already in your brain. So this is the Ebbinghaus retention curve. Here, number of repetitions of the list on day 1 is going along the x-axis, and time in minutes taken to relearn the list on day 2 is along the y-axis, or the one going up. The more times Ebbinghaus practiced a list of nonsense syllables on day 1, the less practice he needed to relearn it on day 2. And the speed of relearning is one way to measure whether something was learned and retained. Like the quicker it takes you to relearn the information, you know that it was learned and retained, at least at some level. And as you can see from the graph, the more exposure he had, so the number of repetitions of the list on day 1, the more that happened, the less likely, the less time it took for him to relearn it on day 2. So if you want to be sure to remember what you're learning for an upcoming test, would it be better to use recall or recognition to check your memory? Why? For the answer, it would be better to test your memory with recall, such as short answer or fill-in-the-blank self-test questions, rather than recognition, such as with multiple choice questions. Recalling information is harder than recognizing it. So, if you can recall it, that means that your retention of the material is better than if you would only recognize it. Your chances of test success are therefore greater. That is why not only am I quizzing you, but I often quiz you so you have to recall the information instead of just recognize it or select it out of a multiple choice. You're welcome. Retrieving a memory. Memories are held in storage by a web of associations. So it's this links to that, links to this type of thing. There are retrieval queues that they serve as an anchor point for pathways that can be followed to access a memory. The best queues come from associations formed at the time of encoding. Priming is activation, often unconsciously, of particular associations in memory. So for instance, well, just like you would sort of prime the pump on a well, you may have never had to deal with a well, but you have to sort of get the suction going by adding some water to the pump that you already have the water, and you add it to the pump to prime it so that the sucking action of the pump will actually work in the well to draw up the water, because there's water that it joins. Priming works in the same way. So priming is sort of like cueing or cluing a memory into working. So priming and awakening associations. After seeing or hearing a rabbit, we are later more likely to spell a word when we're saying spell the word hare. Well, if you see a rabbit, which is also referred to as a hare, you're more likely to spell the word H-A-R-E. Associations unconsciously activate with related associations. Retrieval cues. Memories are context dependent, affected by the cues that are associated with a specific context. State-dependent memory is what is learned in one state can easily be recalled if the individual is in the same state. So, if you're relaxed and chilling in Starbucks while studying for this test, and then later you're nervous when you start to take the test, it would be good for you to try to relax to get to that same state so you can recall the information easier. The emotions associated with the memories have to be consistent. And that's what this is, mood congruent memory, the tendency to recall experiences that are consistent with an individual's current good or bad mood. Retrieval cues and the serial position effect. So there's a tendency to best be able to recall the last and the first items on a list. This explains why one would have large holes in one's memory regarding a list of recent events. Last items in a list are recalled quickly because they exist in the working memory. Time hasn't passed as much, so they're more active. So here, immediately after Pope Francis made his way through his receiving line of special guests, he would probably have recalled the names of the last few people best, which is called the recency effect. But later, he may have been able to recall the first few people best, which is called the primacy effect. So if you look at this graph, you have position of words in a list. So whether they were first, second, third, fourth, fifth, etc., it goes from left to right. And then on the y-axis is the percentage of words correctly recalled. So you can see in the blue, later recall, only the first items on the list were recalled well. That's the primacy effect. But when you ask them immediately, which is the red, the items that were last were recalled best. You can see starting around 9, 10, 11, 12, those were really good. That's the recency effect. So why do you think that would be important? Well, I think it's important because things that you encounter more recently, your brain hasn't learned yet whether or not it's going to be relevant information. So it hasn't decided yet if it's important. So it keeps it active. Whereas the first things on the list, I don't know, I think it's just you encounter it first and you may start rehearsing that, and then you don't have, after you get to a couple, it's harder to do. So I think that's why the primacy effect works. So, what is priming? Priming is the activation, often without our awareness, of associations. It's like a clue or a cue that helps you recall a memory. When we are tested immediately after viewing a list of words, we tend to recall the first and last items best. This is known as the serial position effect. But specifically, recalling the first items is the primacy effect, and the last items is the recency effect. There's some kind of weird thing going on with the slides. Pay no attention to the purple box that keeps disappearing and reappearing. So let's talk about forgetting. Sorry, we can't forget about forgetting. Sorry, I enjoy dry humor. Forgetting and the two-track mind is what we'll talk about first. Encoding failure, storage decay, and retrieval failure. So when do we forget? There are several different stages that has to happen for a memory to get encoded into long-term memory. First, the sensory memory has to be involved. So senses momentarily register amazing detail, as depicted by all these dots that are there. Short-term or working memory then goes through. A few of the items are both noticed and encoded. There may be something about, well, for instance, there may be something about an artistic masterpiece that you look at one time and you notice, and then you go back the next time and you're like, oh, I didn't even realize that part was there. You just don't attend, or you can't attend to all of the information simultaneously. So not everything gets noticed and encoded. And next, the third box, short-term storage, some items might be altered or lost just because your brain decides, well, that wasn't something I needed to keep track of. Retrieval from long-term memory. Some things get retrieved and some things don't. It's just the associations are harder to get to. So forgetting can occur at any of these stages. When we process information, we filter it, we alter it, or we lose much of it. Forgetting in the two-track mind. Humans have two distinct memory systems controlled by different parts of the brain. Reasons for forgetting include an encoding failure. Like we mentioned, we may not even have paid attention or processed the information so that it didn't even get encoded in the first place. There could be storage decay. There could be retrieval failure. And just storage decay is that when your brain decides that the information isn't something that you need to keep track of, so it sort of forgets about it. Retrieval failure is just, it's in your brain, but for some reason the synaptic trail is weak and you can't access that information very easily. This can be with interference and motivated forgetting. We'll talk first about encoding failure and storage decay. So encoding failures are caused by age-related memory decline. Older brains work slower than younger brains. That's just how it is. Conscious attention to limited portions of a vast number of sites. Like I mentioned before, you can't take in everything. It's just too much. And then there is storage decay. The course of forgetting is initially rapid and then levels off over time. Like you'll remember it very easily if you just were exposed to it, and then it is less likely that you'll remember it. It sort of declines that you'll remember it over time, and then it sort of levels off. This is explained by the gradual fading of the physical memory trace. So, forgetting as an encoding failure. We cannot remember what we have not encoded. So, if the external event happened, but we weren't really aware of it, maybe we were looking the other way when it happened, then we're not going to have that information into long-term storage. So here's a forgetting curve for Spanish learned in school. Time in years after completion since a Spanish course. It goes along from left to right, and then percentage of original vocabulary retained goes up from 0 to 100%. Compared with people just completing a Spanish course, those 3 years out of the course remembered much less on a vocabulary recognition test. Compared with the 3-year group, however, those who studied Spanish even longer ago did not forget much more. So it sort of levels off. That's the storage decay. Retrieval failure. Sometimes even stored information cannot be accessed, which leads to forgetting. It stems from interference and motivated forgetting. First, let's talk about interference. Proactive interference is something you learned previously that disrupts the recall of new information. So it's like they're competing for the activation in your brain, and the previously learned thing wins. So for instance, when my husband's best friend got remarried, when I was trying to recall the new wife's name, my brain would give me the first wife's name, and I always had to think really hard. Now, wait a minute, is that the first wife's name or the second wife's name? Because it got mixed up in my brain. Eventually, I learned to call the new wife by the right name. I actually liked her better anyway, so I don't know if that helped. Then there's retroactive interference, and this is when something new you learn disrupts the recall of old information. So that something new becomes more relevant, or something in your brain, and somehow wins in the recalling of the memory. So let's talk about retroactive interference. Here in this graph, we've got hours that lapsed after learning new syllables, and then on the y-axis we have percentage of syllables recalled from 0 to 100%. So new learning in the hour before we fall asleep suffers less retroactive interference because the chances of disrupting it are few. Researchers first discovered this in the now classic experiment by Jenkins and Dallenbach. That's fun to say, Dallenbach. Okay. Day after day, 2 people each learned some nonsense syllables. When they tried to recall them after a night's sleep, they would retrieve them more than half of the items. But when they learned the material and then stayed awake and were involved in other activities, they forgot more. So basically, something else interfered with what was going on in their brain. And you can see that here in the red, after they sleep, without any interfering events, they were able to get encoded into the long-term storage of their memory better, instead of having staying awake and not having that time to process before you had to recall them. Let's talk about motivated forgetting. According to Freud, people repress painful or unacceptable memories to protect their self-concept and minimize anxiety. So repression, according to this theory, is just a basic defense mechanism that banishes from consciousness the thoughts, feelings, and memories that arouse anxiety. Repressed memory lingers and can be retrieved by some clue during therapy. So they're in there, it's just that their brain was trying to protect them from it. Memory researchers think that people succeed in forgetting unwanted neutral information. Like I said before, it's not relevant, so you kind of focus on other things. We struggle to forget emotional events, however, just because they're encoded so well. So, what are 3 ways we forget, and how does each of these happen? So first is encoding failure. You simply just didn't attend to the information, so it never entered your memory system. The second one is storage decay. The information fades from your memory. And third is retrieval failure. We cannot access stored information accurately, sometimes due to interference or motivated forgetting. You will experience less proactive or retroactive interference if you learn new material in the hour before you sleep than you will if you learn it before turning to another subject. Retroactive. Freud believed that we blank unacceptable memories to minimize anxiety. Repress. So let's talk about memory construction errors. There is the possibility of misinformation and imagination. There's something called source amnesia, which we'll talk about, and we will talk about recognizing false memories. Let's talk about errors in memory construction. Memory is not exact because you don't just retrace your memories, you often reweave them, or recreate them. Reconsolidation is the process in which previously stored memories, when retrieved, are potentially altered before being stored again. So all memories are false to some degree. We usually get the main facts right, but some of the details might slip. Misinformation and imagination effects. So the misinformation effect occurs when a memory has been corrupted by misleading information. False memories can be implanted just by hearing a vivid retelling of an event. If your friend tells the same story that you were a part of, they may remember something differently or have a different perspective because they were looking at it in a different, oriented in a different way, and that then influences the memories that you have. There's also the imagination effect. This occurs when repeatedly imagining fake actions and events that creates false memories. You just think of it so much, you're not sure if it's real or not. So let's talk about memory construction. Some researchers did an experiment and had people view a film clip of a car accident on the left. So this is the image of the actual accident. Those who later were asked a leading question, which is sort of worded in a way that talked about the destructive damage of the situation, recalled a more serious accident than they had witnessed. So the question, it's actually right here on the slide, about how fast were the cars going when they smashed into each other, which primed them to think about, wow, they were going pretty fast, so they were pretty smashed. So people in the experiment were more likely to recall what they saw as being more severe than it was. There's also something called source amnesia. This is faulty memory for how, when, or where information was learned or imagined. This helps explain deja vu, which, remember, that eerie sense that I've experienced this before. That eerie sense that I've experienced that before. Sorry, I couldn't help but repeat it in a deja vu kind of manner. So, cues from the current situation may unconsciously trigger retrieval from an earlier experience. let's quiz ourselves. What, given the commonness of source amnesia, might life be like if we remembered all of our daily experiences and all of our dreams? Well, basically, real experiences would be confused with those that we dreamed. When seeing someone we know, we might therefore be unsure whether we were reacting to something they previously did or to something we dreamed that they did. Recognizing false memories. So false memories are hard to separate from real ones because they seem real. They can be persistent. Repeated retellings of an event may make individuals feel like they had actually observed the event. People easily remember the general idea rather than the exact words. Thinking critically, part 1. So there are challenges related to adult recognition of childhood abuse. People doubt childhood sexual abuse survivors who tell their secret. Just because, why did they wait so long? Or, are you sure this really happened and you're not trying to get attention? Innocent people are often falsely accused. Therapists prompt recovered memories or repressed memories of childhood abuse. Professional organizations have agreed on the following. Child sexual abuse does happen. It just does. Injustice also happens. Forgetting happens. Recovered memories are common. Memories of events before age 4 are unreliable. The brain just isn't as structured to remember things. Memories recovered under hypnosis are especially unreliable. And memories, whether real or false, can be emotionally upsetting. Let's talk about children's eyewitness recall for a moment. Researchers studied the effect of suggestive interviewing techniques, so saying something like, victims of sexual abuse often have your symptoms, so maybe you were abused and you forgot about the memory. Let's see if I can help you recover the memory by digging back and visualizing your trauma. So that actually almost motivates the person to come up with the situation, and that's come up with being abused. And it's true, 58% of preschoolers produced false memories about one or more unexperienced events. They knew they didn't happen, and but because of the way they were interviewed, they thought or recreated or just said that they happened. Children can accurately recall events and people. It occurs when a neutral person asks non-leading questions soon after the event. So, imagine being a jury member in a trial for a parent accused of sexual abuse based on a recovered memory. What insights from memory research could you offer to the jury? It will be important to remember the key points agreed on by most researchers and professional associations. First, sexual abuse happens. Injustice happens. Forgetting happens. And memory reconstruction happens. Recovered memories are common. Memories from our first 4 years are not very reliable. Memories claimed to be recovered through hypnosis or drug influence are especially unreliable. And memories, whether real or false, can be emotionally upsetting. So take all of that information and factor it in the next time you hear about someone being sexually abused. Don't discount them, but just factor in all of these things, because it may be true. The point is to get at the truth. So how do you improve memory? Rehearse repeatedly. Make the material meaningful. Activate retrieval cues. So prompt yourself with certain things that will get the right answer. Use mnemonic devices. Pretty please, my dear Aunt Sally, for instance. Minimize proactive and retroactive interference. So when studying for a certain something, don't study for the next thing right away. Sleep more, because that's the time when your brain puts things into long-term storage. And test your own knowledge. What's the best way to retain new information? Think actively as you read. That includes rehearsing and relating ideas and making the material personally meaningful. So, which memory strategies can help you study smarter and retain more information? Spending more time rehearsing or actively thinking about the material to boost long-term memory. Schedule spaced, not crammed, study times. Make the material personally meaningful with well-organized and vivid associations. Refresh your memory by returning to contexts and moods that activate retrieval cues. Use mnemonic devices. Minimize interference. Plan for a complete night's sleep and test yourself repeatedly. Retrieval practice is a proven retention strategy.